Good morning, good afternoon, and good evening, wherever you may be in the world. Thank you for tuning in. Welcome to my channel. We are focusing on cubic functions and hyperbolas in this particular lesson, and it is a continuation of our exam preparation series for mathematics paper 1. I believe you have your pen and paper with or your notepad so that you can work along with me as we entertain or interact with this particular question. All right, so there are a number of sub questions that we're going to answer, and let us see what's in store for the first one. Take a look. Okay, so we are given two functions, a cubic function as well as a rational function, or a hyperbola if you like, and we are also given some points that are indicated with -3, 1 over 2 as the x-intercepts of the cubic function, as well as the y-intercept of the cubic function at 9. Now, the equation of the cubic function is given in variable format, and the question there is asking us now, what we're required to prove is to prove that the values of a, b, c, and d are exactly these numerical values. Okay, how do we start? This one is straightforward, comes in there because it is the y-intercept. Okay, so the proof, the solution of this question, I'm going to say d is equal to 9 is the y-intercept of f. Okay, so we don't have to do anything more. However, what do we notice? F has two x-intercepts, okay, and at -3 there's a turning point there. And if you recall nature of roots, where we dealt with a parabola, when there's a turning point at an x-intercept, or it just touches the x-axis, that is actually two roots that are equal, or we can say one double root. Okay, so we're going to have x plus 3 all squared, okay, times x minus half as the equation for f. Okay, then x-intercept of a root at -3 and also at half. So the format of the function f is like this. Now, what do we need to solve for in this case? We have a y coordinate from the y-intercept that we can substitute here, 0 for your x coordinate coming from the y-intercept. So let us do it, because doing so will allow us to solve for a, 0 plus 3 all squared, 0 minus half. Okay, so what's going to happen here? We're going to have a 9, right? Because it's 3 squared, you divide both sides by 9, you get 1 this side. This will give you a -half, and therefore if you multiply both sides by -2, you're going to get a is equal to -2. Okay, so this is the second variable that we've just proven to be indeed -2. Okay, so what do we do now? We go back and substitute the a value, -2. We can expand this because now we're moving in the direction of values of b and c. Okay, so this will be x squared, square of a binomial, plus 6x plus 9. Okay, it's x minus a half. Okay, so we need to work carefully here, and let us leave the 2 there for now. So it's a trinomial multiplied by a binomial. Okay, so let's work carefully there. x cubed, x times 6x, 6x squared, x times 9 plus 9x. Okay, let's deal with the -half. Multiply there, minus half x squared, multiply there, gives you minus 3x. And then you multiply this one as -9 over 2. Okay, we need to distribute the 2 now into the brackets, and if we do so, or we can collect the like terms, that's fine. Let's start with that. And what else? This guy and that guy. Okay, so negative 2 to x cubed 6 minus 1 over 2 gives you 5 over 2, right? Oh, sorry, 5.5 x squared, and 9 minus 3 is 6, and we're done with those two. We have minus 9 over 2. Good. Now we are ready to distribute the negative 2. If we do so, get a negative 2x cubed. When you distribute there, what do we get? Negative 11x squared. You distribute there, negative 12x. You distribute there, you get a positive 9. Okay, we get your b value. Okay, it's negative 11. You get the c value, it's there, and it's negative 12. So therefore, we have proven that indeed those variables have those particular numerical values. This takes care of A1 of the main question, question 9. Let us go to A2 now and find out what's in store. Take a look. Okay, so we need to find the x-coordinate of f. We are told in the question that f is a point of inflection. What do we associate that with? Second derivative, you're right. So let us go for it. We need to derive this function twice and be able then to get the solution to the question. 3 times negative 2, negative 6x squared, minus 22x minus 12. Okay? F double prime x is negative 12x minus 22. Right? So at f, what do we know? F double prime of x is equal to 0. Okay, point of inflection, negative 12x minus, this must be 22. Okay, let us just correct that, is equal to 0. So we have negative 12x equal to 22, and you divide both sides by negative 12, and x ends up being negative 11 over 6. Does it make sense for the x-coordinate of f to be negative? Yes, it's on the left-hand side of the y-axis or of the origin. So definitely the x values there will be negative. Great stuff. This takes care of A2. Let us go to question B. Here it is. Alright, so in this question we are asked to find the coordinates of E, which is a point on F. However, we are told that the gradient at point E is 8. What is the expression that represents the gradient of the function? It's this one. Okay, so we're going to take this one, equate it to 8, solve for x, and get the corresponding y value. Okay, so therefore at E, we have negative 6x squared minus 22x minus 22 equal to 8. Negative x squared minus 22x minus 20 equal to 0. If you plug this in a calculator or apply the quadratic formula, you're going to get x equal to negative 5 over 3 or x equal to negative 2. But if you compare these solutions to the previous answer that we got for the x-coordinate of f, you'll see that x equal to negative 2 is the right one. Okay, it cannot be this one definitely. So we see that the x-coordinate of E will be negative 2. How do we get the y-coordinate? The y-coordinate of E will be f of negative 2. And if you plug that in the original function expression, you're going to get 5. Okay? Therefore, E has the coordinates negative 2 and 5. Okay, does that make sense? Yes, because it's above the x-axis, it should have a positive y coordinate. Okay, so this takes care of our solutions so far for F. Now let us also talk about G. That is the next question. All right. So take a look. Okay, so now we are given a context where G has a vertical asymptote at the minimum stationary point of F. Where is that taking place? At -3. So if you plug it back into the function, it becomes +3. Alright, so it means here that G of x is actually 2 over x plus 3 plus q. Nothing was said about the horizontal asymptote. That is still unknown. So what can we do? We recall that point E is not only a point on F, it's also on G. So we substitute that into here. G of x is equal to 5, equal to 2 over -2 plus 3 plus q. We have 5 equal to 2 plus q, and q is equal to 3. So therefore, g of x is equal to 2 over x plus 3 plus 3. Okay, so that was pretty much straightforward. And this takes care of question C. Okay, so that was C. Okay, good. Let us go to the next one. Okay, the next question is asking us to get the equation of the axis of symmetry with a positive gradient. Okay, so that is standard. We know that it will be some equation of this sort where we need to solve for its y-intercept, because now the gradient is already 1, which is a positive gradient. Okay, you need to know that the hyperbola has a center determined by the intersection of the horizontal and vertical asymptotes. Okay, so what will be the center here? -3 and 3. Okay, so you substitute these coordinates in the equation, and you will see that C is equal to 6, and therefore the equation that we're looking for is this one. Okay, pretty much straightforward as well. Okay, let us now go to E. Take a look. Right, so this type of inequalities definitely needs us to read the graph from left to right. Okay, and see where is F above G, or where are they having a common point, or we're talking about a point of intersection. Okay, F being equal to G. Good. If we start here on the left hand side, or we can say -infinity. Where is G? There it is. Where is F? There it is. Definitely F is above G. And if you trace or track the progression, you can see all the way to the vertical asymptote -3, F definitely in this interval is above G. So x is an element of -infinity all the way to -3. You cannot include -3 because G is undefined there. What happens after -3? So we have G here, F is down here. That is not what we're looking for, okay? But are we looking for the point of intersection? Yes, where F is equal to G, and that happens right here at -2. So we're going to take -2. Okay, after the point of intersection, what is happening? F now is above G all the way to the origin or 0. Okay, there was a restriction given in the question. We're only looking at -infinity to 0. We're not going to look at what's happening that side. Okay, so we're going to now have another interval here from -2 all the way to 0. All the way to 0, okay, where F is still above G. So that takes care of this type of questions, and it is usually a standard procedure. Left to right, trace the graphs, and you will be able to get the right answers. As long as you have values for your important points, that becomes the reference points. Okay, this takes care of this question. Let us go to the last question of question 9. Take a look. Okay, so we are given a new function h, such that it does not intersect the graph of g, the red one, for x greater or equal to 0. Okay, so we're going to look at what happens here from the y-axis to infinity. And then we have 2 points to refer to, the y-intercepts of f and g. Okay, we know that the y-intercept of f is definitely 0, 9, so that y-intercept of g, if you substitute 0 in the equation of g, you get 2 over 3 plus 3, giving you 11 over 3, 0, 11 over 3. So the difference here is what the k value must be less than. In other words, the graph to shift down by less than that particular difference. What is the difference? It's 9 minus 11 over 3, giving you what? 27 over 3, right? Giving you not 27 over 3, 16 over 3. Okay, so it's 27 over 3 minus 11 over 3 basically. But in any case, that is the difference. However, the graph must not move up because it will still intersect the graph of g because it's going to negative infinity. So the graph must move down by units that are less than negative 16 over 3. The negative is important there because it shows that it's going to be a vertical shift downwards. Okay, so yeah, that was the reasoning behind this one in terms of function transformations, okay, where you don't want a point of intersection for the domain x greater or equal to 0. Thank you guys. This was a long video. Remember, for each video for exam preparation, series especially, you need to watch it from start to finish because maths is about connecting concepts. One leads to the other, so you don't want to take shortcuts there. All right, so thank you for tuning in. Look forward to the next video that will talk about 3D objects. So I'll see you on the other side. Keep well. Sharp, sharp.